Thank you. So I'm going to tell you, the story I'm going to tell you is about things that, although they were born in the string theory community, and I will tell you why, they belong to us in reality, to StatMech normal thinking. So quantum bounds. So So imagine you have hard particles, and then I have two walls to which I stuck some half particles to make it rough. And this is classical, and so I want to understand the viscosity of this thing. And viscosity is the transfer of transverse momentum. And of course, this is because the particles get some momentum from one wall, and because they move, they take it to the next particle with which they collide, and so, and you see that this process is going to be in a way proportional, or so grow with the temperature, because the way that a particle has to go and walk to the next one and give it its momentum depends on how fast it is moving. And so when you are in a classical case and you take the temperature to 0, so particles are really not moving, except, well, they are slightly reaccommodated by this motion, but to the extent that this remains a 0 temperature situation, the viscosity drops down to 0. However, if now I switch on the quantum mechanics, what happens is something else. You can see it from 2 points of view. One is that two particles do not want to be very much together because they don't want to squeeze a quantum wave beyond de Broglie length. We know this because we all solved the square well, and we know that when we squeeze it, the energy goes up. Another way of saying the same thing is there is a 0 temperature kinetic energy. So the idea, this very simple example already gives you an idea, and there was a conjecture that originated from string theorists that if you divide the viscosity by the entropy density, this is always going to be bigger than something. This something, h bar, well, no, let's wait a second to say what this something is. But, okay, so why these people found this magic, and I will come back to this again, is because the models that they had for black holes, which are very toy models, saturate this bound. So this game is played on two levels. You want a bound, and then you're particularly interested in things that saturate it. Things that saturate are things that are related to black holes, holography, and what have you. But if you have, I don't know, quark-gluon plasma or something like that, or even a solid-state system that goes close to the bound, then you can start dreaming of maybe something in holography is going to help me in this subject. So it is a symptom. Now, nobody was able to prove this except verify it, and I will come back to this, but it's not even clear if it's true. There are counterexamples, but when you talk to people, some of them don't like the counterexamples, and okay. Now, this was the situation until, I didn't put the name, but Maldacena, Shenker, and Stanford decided to look at another thing where a bound could possibly exist, a quantum bound, which is a Lyapunov exponent. So we have to first spend a minute defining a quantum Yapoon exponent. We have no trajectory, so we have to think what we're going to do. This was done for us by Larkin and Ovshinnikov many, many years ago. But the best way to put it is the following. You have a packet or whatever, you evolve, and now you kick the system and evolve it back. You can do this in the computer and even in some experiment. This is called the Loschmidt echo. And you realize that the difference between what comes back and what went is a nice definition of a Lyapunov exponent. But now you can do it quantum because there's nothing that forbids you from evolving, kicking, and evolving backwards. So here you have a nice definition, And now you measure, you do this is what I'm doing, A, and then I evolve it forward, then I give it a kick, and then I evolve it backwards. And then I measure the difference from what came back. This is a measure of this distance here. And you realize that what you get is the commutator of the two operators squared. And now Larkin and Ovshinnikov tell you, well, but if you have a commutator square with a Gibbs measure, now I know how to make it classical, and this is the Poisson bracket square. But the Poisson bracket square is a classical definition of the Lyapunov exponent, so we are good. We have found here a nice definition of a quantum Lyapunov exponent. And now, okay, and remark, it is a four-time function, because if I do this square, AT, B, AT, B, etc., there are going to be four operators at four different times. And these gentlemen here proved this bound, that the Lyapunov exponent has to be smaller than this quantity. So as you go to zero temperature, it goes to zero, but as h bar becomes larger, it also depresses the value. So, and let me say it now, and I will repeat it as many times as h bar over t is what I'm going to call the Planckian scale. It's a thing that has dimensions of time, and it's model independent. No, h bar over t doesn't talk about the model. This is what we call the Planckian scale. So basically what they proved, and this one they did prove, is that the Lyapunov exponent is bounded by the inverse of the Planckian scale, under certain circumstances that I will tell you. Now, yes? This is equilibrium. Yes, you are at temperature T, and you calculate this commutator squared, and you conclude, and you will see this, that this is bounded, I mean, the exponential growth of this commutator squared is bounded by the Planckian scale. No. Like all Lyapunovs in life, they depend very little of the operators. Okay, so when you go to the proof, first of all, you say, and this is the nice thing, their models of black holes saturate this bound again. This is why they are excited. But we are excited not for so much for that, because it doesn't talk to us very much, but the question is this a string theory result, or is it just StatMech plus uncertainty principle? And this is what it is. So this is why I'm talking about this here. So the proof is, you can follow it. It's one of those proofs where you follow 6 steps. Each one of them you swallow, but by the time you go to the 6th, you're a bit lost as to what was the whole thing about. It involves analytical continuations in complex time. So we thought that this merited an easier explanation, and indeed it does. So before that, I need to do this little technical thing, unfortunately. So what your object, you're given, is the commutator square with a Gibbs measure. Now, Maldacena, Shenker, and Stanford introduced, and this turns out to be quite important, a regularized version in which you see, instead of having the square and the Gibbs measure, you have a quarter, one of the commutators a quarter, and then you square it. So you're chopping up the Gibbs measure. It's a regularization, let's say. And this one is another one. Also, they come classically, clearly they are the same, because you can move all the Gibbs measure, they commute, and you can move it to the end. But we will need version 2 and version 3, and indeed the original proof also needs version 2 and version 3. Okay, but let us for the moment say this is not a big deal. It's just 2 regularizations, okay? Okay, so again, I'm repeating this. The point here is that the motivation is that black holes and systems that come from holography, whatever, are expected to saturate these bounds. And this is very important for them. Then something amazing happened, is that Kitaev realized that a very simple quantum spin glass model did the job, saturated the bound and all that. So immediately, because this is a symptom, this model was promoted to being a kind of toy model of holography, black holes, and what have you, with the important difference that here you know how to calculate everything. So this, it made the field a bit explode, but I'm not going to get into this, but it's an interesting part of the story. Okay, so once again. Okay, so let me make a small detour on fluctuation dissipation, which was mentioned several times here. Well, the classical one you know. You have the Poisson bracket between two things, and then you relate, you can define this way the response, you have the correlation, and the classical fluctuation dissipation relates the response with the correlation. And we will work a lot with the integrated response, which then, integrated over time, which then is directly proportional to the correlation, so no derivatives. Okay, so why is this important? This is not just, some equality that can help us in some occasion. This is crucial. If I connect a thermometer to many copies of a system, the same observable in those many copies, and I ask myself, what will happen? What will the thermometer read? I would like it to read, these are equilibrium systems, to read the temperature of the system. But how does energy talk to this thermometer? Well, noise will move, will agitate the thermometer, thermal noise, and friction will stop it. This, as you see, I am remaking Einstein's argument for Brownian particles. And so this balance between these two things work and give you the temperature thanks to fluctuation dissipation. Okay, so although, and this is quantum too, because it would be a catastrophe if quantum mechanics broke this. If fluctuation dissipation doesn't work, forget about thermodynamics. That's the point. Okay, so now quantum. Well, quantum, it's a little bit more difficult, but not so much. You take the Gibbs average, and then the correlation, you can show it and argue it, etc., is the expectation of the anticorrelator. I'm sorry, these brackets are not Poisson now, it means anticommutator, so AB plus BA. The response is the expectation of the commutator. This is what you're taught in, and this you can construct it and give a kick to the system and see what happens and do it. And then a new object appears, which will be important for us. It's only quantum in the sense that if this were classical, I could just put this thing on this side and I will get the same original stuff I had at the beginning. But in quantum mechanics, I cannot. This is a chopped measure. You see, I put half and half. And this is a very nice object, and it will be very important for us. It's a purely quantum thing. For the moment, it's a mathematical thing, but okay. Just for a bit of background, that object there, when you are in a quantum chaotic system and you diagonalize your Hamiltonian and you look at the matrix elements of any local operator, it has a bandy form. It's zero far away from the diagonal. It has kind of a band form. And indeed, the distribution along this band is precisely this F I've defined before, which is its Fourier transform. So it has a meaning. Okay. So let me go on with fluctuation dissipation. So you have the correlation, you have the response, and now you can prove the fluctuation dissipation theorem, which now is similar to the one we all know and love, but with a twist. So the way you find it in books is this one. The response is this tangent times a correlation. If you develop the tangent, you get in powers of h bar, you get the usual fluctuation dissipation. If not, you have to live with this one. But now I am going to use the fact that we introduced this f function, which is sort of midway, and you can write it in two steps. C is this, R is this. Of course, if I divide these two relations, I get this one. But I prefer these two relations. Why? Because the cosine and the sine are analytic functions rather than the tangent, and it will be useful for us. Okay? So, yes? Yes, well, first of all, the thing I told you about the band structure of ETH, eigenstate normalization. But also, you will see now, fluctuation dissipation relates, you can write it as you shift the time axis and you say something above and something below are the same. This is KMS. Well, this line where you put things is the line of F. So it's the symmetry that is involved in KMS. Okay, so the usual fluctuation dissipation, as we said, is a relation between correlation and response. Here, you make an intermediate stop on this function, okay? Why? Because you will see that you learn a lot from it. And then you have some operators that take you to one side to the other, which are, of course, nothing but this. Okay, so let me look at the ones that take you away from F into R and into C. You can write them this way. So cosine of a derivative means that you do the expansion, the Taylor expansion of the derivative. And this relates C with F. R is related with F in this way. And for example, you can use this because if F happens to be an exponential, you can compute these successive derivatives. And fluctuation dissipation tells you something very simple, that C is now not the cosine of a derivative, is the cosine of the actual exponent, and R is the sine, and you can divide these two so that you find in time that C over R is the tangent of the exponent. So for an exponential, this is particularly nice and easy. Okay. And you see these operators are a little bit nasty in time. These are the same as the cosine of omega I wrote before, no? But here it's a time derivative that is iterated. You can do it, I'm sorry. So for the exponential, as I told you, they act in a very controlled manner and give you a cosine and a sine, simply. No, cosine, because there is an I in the game which sort of arranges things. And it will be important. Now, the inverse ones are rarely, or if ever, found in books, or I would say never. So these are the inverse guys, the ones that, and you can show that F is related to C through convolution with this object here. Omega is the Planckian scale, here and in what follows. So you see you're convoluting with something, and this gives you F, and psi is the integral of the response, which I told you is a nicer object. Psi is related to F this way. And you see that when the Planckian scale collapses, this is a delta function, morally, and you get these identities, which are the usual classical FDT. So it's nice, and we will come back to this, to see these things in time this way. As this is just repetition, you're convoluting with this bell shape, which is 1 over cosine, whose width is the Planckian scale. And you see, your correlation or your response, integrated response, is going to be blurred with this quantum convolution with a thing that has a width. That is the effect of fluctuation dissipation. And they become deltas in the classical limit. Okay. Having said this, this is just a recap of the ordinary fluctuation dissipation theorem, KMS, in quantum mechanics, Kubo, Martin, Shenker. Okay, fluctuation dissipation and bounds. Here comes the proof in its easiest form. This was partly done in a work with the group of Ueda, Tsuji, and it's a work we've done with Laura Foini and Silvia Papalardi. So you need to calculate things like this. Remember, there was a commutator squared. So this is one of the many terms you have. And now, this is a 4-point function. As I told you before, it comes from a commutator squared. This is one of the many terms of the commutator squared. And you have a 4-point function, but we don't like 4-point functions because when we talk about fluctuation dissipation, things like that, we usually talk about 2-point functions. No? So, yes? Okay, this is just the definition of one of the many terms that come when you develop the commutator here. Remember, you wanted to calculate things like, sorry, you had many terms coming from here, yes? This if you develop it's a different squared, no? So it has 4AB. You develop the anti-commutator squared. So it gives you many terms, okay? One of them, but just to show, I took one of them, which I call S, because it's absolutely nothing to do with entropy. You see, the commutator comes from this term and this term. Then, of course, there will be a BA, AB, then there will be a BA, BA. There are 2 to the 4 terms that I have to calculate. This OTOC means out of time order correlator. Yeah, because it's you're not accustomed to have time 0, time t, time 0, time t. This is why it's called. But it's one of the terms of the commutator, shown here as an example only. Now, so because we don't like the 4-point functions, there is a trick that exists everywhere a bit in quantum mechanics, which allows you to go from 4-point functions to 2-point functions. It lives in several versions, but you can, if you want, this is what you're calculating. I just rewrote this one. But if you now make your space a product space of twice the same space, so you duplicate the space, you can, and this is just a standard trick, write everything as a 2-point correlation. This one becomes a 2-point correlation in a fatter space, which is the Cartesian product or the tensor product of the state of the Hilbert space with itself. Okay, this takes you 10 minutes to be completely convinced, but the only morals of this is you can always take a 4-point function and take it into a 2-point function. Why do I want a 2-point function? Because fluctuation dissipation and such, which is what I want to use, I know it with 2-point functions. Okay? So this same object now reads in this product space this way. P is the swap operator that takes an operator from space 2 and sends it to 1, or 1 to 2. And now something remarkable happens. The quantities you want to calculate are exactly a correlation, a response, and an F in this duplicated space. Miracle, miracle. So this is just the definition I did before, but in the duplicated space, doubled space. So I have anti-commutator, commutator, and this intermediate stuff. And then when you develop them, you get something in black, which we will be neglecting. And precisely here, the quantities, the version 2 and version 3 that I started with, that gives me the Lyapunov exponent. Miracle, miracle. So these two quantities are obtained from correlations and response in another space. But now, in this space, it's a correlation or response and one of these split functions. Where is row? Second line. Here?
2 lines below.
Ah, sorry, it's a Gibbs measure. It's e to the minus, so to the 1/4 is the split one. Yes, thanks. Okay, so the quantities we wanted to prove something about, these are two versions of regularization, this is why I had to introduce them, are a correlation and this F function, and you could also write a response here. I didn't because we are not going to use it, but you could also do. And then here you join Maldacena, Shenker and Stanford in the fact that they also use it in their proof, that this quantity is a completely innocuous quantity because it has all the things in one time here and all the things at time 0 on the other side, and here too. So these quantities are not interesting. They are just a 2-point correlations morally, and the idea is that they will decay much longer before the Lyapunov times that we are interested in. They also did this assumption. So basically, the red parts, which are the nice things, the regularized versions, are a correlational response and an F, there's a third line here, in a certain doubled space. And the quantities that are regularized have the beauty that you see that they're positive definite, because they come from squares. Okay? And now you're done. With all this rewriting, you're done, because these things grow as Lyapunov. But now when you look at the relation between these two, because it is a C and an F, there is, I told you about when you have an exponential, the fluctuation dissipation quantum comes as a cosine. And so the fluctuation dissipation gives you this relation. It's the same thing I did before, but as applied to this quantity. But now we have a problem because C and F are positive. These two. So, and a cosine is not always positive, precisely, and it would lead you to contradiction if this thing became negative. And if this thing becomes negative, you are violating the bound. So the bound is nothing else than saying that two positive quantities related by fluctuation dissipation, of course the relation has to keep the positivity, and because quantum mechanically there is this cosine, whatever is inside has to be smaller than pi over 2. So that's a bound. Yes, it is obvious in some systems. So precisely, now that I'm here, there is a beautiful paper by Christophe and Harald Posch, where they explicitly do classically with disks, and they see that with disks, just by playing with their sizes, you go from a regime where this happens to a regime where it's exactly the opposite. So everything is possible. The Lyapunov time can be larger or smaller than the collision time. Scale larger or smaller. Theirs is a concrete example of that. But for the models that these people like, and this is an assumption of the theorem, otherwise the theorem doesn't work, you have to be able to throw those bits. Also in the original proof. Yes, exactly. You assume that both grow, and this is physically reasonable, in the same way. They diverge in the same way, and then you conclude that you have the... Exactly, and the lambda by hand requires knowing something about the system. There are many, many, many quantum systems. I would say most quantum systems don't have a Lyapunov regime. But you are bounding something, so you have to assume it exists. That's not stupid. There are ways. You can go continuously, which I will do here. And you know that you're starting, that you're starting from the first quadrant, and then it goes up and it hits the bound there. This is an argument of continuity. Somehow you have to argue something like that. Can you invent a bizarre system so that it jumps? I've never seen it now. Yeah. Okay, so what happens is that, for example, as you go down in temperature so that the Broglie length grows in a system, you hit a point at which a Lyapunov that is inversely proportional to the typical speeds, boom, would violate your bound, but there quantum mechanics intervenes in some way or other, but you've proven it's general, and then under the assumptions I made before. I want to underline that the assumptions are exactly the same of Maldacena, Shenker, and Stanford. We didn't add anything. The only thing that we did is their analytic continuation and a complicated argument in the complex plane for us became fluctuation dissipation. Now, okay, but remember that it's not the Lyapunovs that were the original motivation, it's transport. So what about transport? I mean, this is the first instance where such a thing has been proven. But, okay, what do we do with transport? Transport, as you all know, is you have a current-current correlation, and you want the area under this curve. No? This is the integral of the current-current correlation. So you want the integral under this curve to be as small as possible, let's say, if you want to show. And the bound is telling you that you would like to bound it with something that has to do with h bar. And the idea is to say this curve cannot, to have a very small conductivity or viscosity, corresponding transport coefficient, you need this curve to fall rapidly and have a small area, for example, or arrange itself to have a small area, in any case, a small integral. Now, the idea is that quantum mechanics doesn't allow you to do so. But as I say, nobody has found a proof, and it's not even clear under which assumptions such a thing would hold. However, one thing we get from here that wasn't in the original proof of Maldacena, Shenker, and Stanford is that the crucial element for this to hold, for everything, is quantum fluctuation dissipation. So it has these, yes, and I would say, but there I have a problem. I have tried to work for finite systems because they are interesting. In quantum, they are especially interesting. But even saying that something decays exponentially doesn't work or grows. Things tend to oscillate when you do. I don't know general results, and I don't know to whom I should ask. But I don't even know to whom should I ask. But when you try to make a finite version of a model that has an exponential growth, you discover that it has oscillating terms. So even the very beginning, even defining a Lyapunov is a bit not very nice. So I am a bit lost on that point. Yes, yes. And this brings us to another thing. Remember the bound I put on viscosity, which we don't even know if they exist, but the one that was postulated is the viscosity divided by the entropy per unit particle. What do I know? I mean, the bound could have something else below. So what is in the proportionality constant? Even that is not clear. So is there a bound? Question one. Question two, what is the exact form of that bound? What is the proportionality constant? So somebody who believes blindly would answer to you, yes, but you know, when it's an insulator, there's a prefactor in the whole thing that will go to zero. I don't know. But the tough part to prove is the area, no? The other part is supposed to be an equilibrium quantity. So quantum FDT deserves a better look. And well, can we find, because remember, the point is that the transport is a question of 2-point correlations. It's really a question of 2-point correlation, not 4-point correlations. We managed to convert a 4-point correlation into a 2-point correlation, but in the process, we found that two quantities were positive definite, and that was crucial for us. Here, you don't, in general, have such things. So what do? Well, first thing you can convince yourself is that just by considering a pile of oscillators, just independent oscillators and different oscillators with frequencies that you like, you can always do that system. You can convince yourself that essentially you can have the correlation and the response that you want. You can construct there are basic constraints on signs, but other than that, you can construct the correlation and the response that you like, just by putting correlators one on top of the other, yes. So there can be no bound that is general for correlation and response, because you give me something you like and I make it for you just by piling oscillators of appropriate frequencies. So surely there is no bound on the decay, a universal bound on the decay. So something more has to enter the game. So the first morals is don't expect a super general bound. Something you will have to put. So maybe, Abhishek, your insulator will be out of my bound the day we will find it. No? But I would like to emphasize the basic mechanism. Remember that I told you that fluctuation dissipation, this function that takes you from one place to the other, is a convolution of your correlation or your response in time with this 1 over cosine squared, hyperbolic cosine squared. So it acts as a blurring function. So this already seems to be telling you that if your response had, very steep changes, somehow when you go to the correlation, you will lose them, and vice versa. So there is this blurring that seems to be at play, or at least one of the leads that we are trying to follow. Another thing that I find is quite fascinating, and I don't understand the deep meaning of this, is that if this is an exponential that falls, if it falls fast enough, and you are convoluting with this, if this exponential of the system fell more rapidly than the Planckian rate, the Planckian time, then this convolution is no longer dominated by around this point. It is dominated by the very short times. So if something falls super fast, faster than Planckian, everything that happens at long times is dominated by the short times. What is the meaning of this? I don't know. I mean, when you talk to conformal people, they are happy because in their stuff, short and long agree, but for non-conformists, this is strange. And in the case of something growing, the opposite happens. If the growth is super Planckian, then again, this thing is the one that late times dominated. So I don't know, these are all leads that we are trying to follow. Of course, if this is a smoothish function and you're going to a narrow case, so you're going to the classical limit, convoluting with this Gaussian is the same as essentially evaluating in the point, and you tend to either the classical fluctuation dissipation or some little fluctuation thereof, some correction thereof. Okay, this is the kind of thing that is interesting because it gives us a perspective of what fluctuation dissipation does. Will it lead to some form of bound to transport coefficients? We don't know. People are divided on this. Is there a true, and if there is a true one for transport, what does it entail? You can construct counterexamples, so it's not clear what are all the elements that enter into such a proof, and it's not clear if there is such a proof, or if the fact is true. But there are lots of people who believe, and you will find this in books, that the Planckian beta h bar time is a limit to the speed at which you can do things, for example, thermalize. But it's the same idea, the same problem, because of course, if you have a big thing, conductivity will tell you how long it takes you to thermalize. Can we prove something about it? I believe probably, but it's not that we don't know how to prove it, it's that we don't know exactly what to prove. But we know the general direction. And in our case, I mean, Silvia, Laura, and myself, we believe that fluctuation dissipation is going to be at the heart of it. Thank you for